computer. All right, welcome back to Organic Chemistry 2341, Organic 1, and we're going to continue on with Module 7. We're going to start with 7.2 right now, which is additional reactions to form alkenes. 7.1 was all about the E1 mechanism, and the E1 mechanism always goes through a carbocation, okay? But there's the possibility of not going through a carbocation, and that's what we call our E2 reaction, okay? All right. Oh, shout out to those who are going to be just watching the video. We have a group activity next Tuesday on SN1, SN2, E1, E2, and we have our exam next Thursday. So start studying for that exam. All right. So let me go ahead and share my screen and get started. Oh, it's not going to share because I didn't plug in my iPad. Let's see if it's going to share. Yes, it's sharing. That's wonderful. Okay, so the E1 mechanism is all about forming a carbocation and then picking the beta hydrogen, the hydrogen 1 carbon over, that gives us the most stable alkene form, our most substituted alkene form whenever possible, okay? Now, our E2 reaction is going to be a little different. Although it's going to try to do that, we can actually make it not get the most stable alkene out of it. So we're going to talk about that and compare and contrast that. Let me go ahead and move my video over here. All right. So as the name suggests, the E2 reaction is going to be a bimolecular reaction. So the base and the electrophile are going to be there at the same time. So when our nucleophile is also a strong base, we can actually have it remove a proton and then lose the leaving group, and instead of doing the substitution reaction, okay? However, which mechanism, the E2 or the SN2, depends on the substrate, okay? So if we look at the first substrate here, we have our primary alkyl halide right here. We have a good nucleophile and a strong base. So what we've done is we've taken that proton off of alcohol. Our alcohol has a pKa of 16, 17. So that means that this has a pKb of like -2. That makes it a very strong base, okay? So because it's a good nucleophile and a strong base, it's going to be in competition with the SN2 reaction and the E2 reaction. But the defining factor here is we have a primary alkyl halide. Our primary alkyl halide, it does not have a lot of steric demand, and therefore the SN2 dominates on this one right here. So in your primaries, even if you have a good base, you will get a significant amount of the SN2. It will be your major product. But note, you do get some of the elimination product right here, the E2 product, okay? That's because it's such a strong base, okay? So when we have our primaries, think that it can act more like a nucleophile than a base and give you the substitution product as the major product. Now, let's compare that to going to a secondary. When we go to a secondary, now we have two methyl groups that are blocking that attack from the opposite side of the bromine right here. And remember, they have to be able to flip over in the SN2 reaction and invert there. So we now have two methyl groups that are interfering with that nucleophilic attack. That makes that attack slower than the elimination product, okay? So if it's slower than the elimination product, it's going to be, excuse me, let me take a sip here. It's going to be the minor product because of that steric demand, okay? And notice we're using a similar base here. This is just the deprotonated form of ethanol to make our ethoxide as our base, okay? So we do get, oh, this should be a CH2, CH3 here, okay? We do get some of that substitution product, but the major product when we have a secondary alkyl halide is the alkene or the elimination product, okay? Now, once we get all the way to our tertiaries, right? Remember, the rate of our tertiary here is like 1,000 times slower than our secondary. So we effectively get 0% of our substitution product, and we get 100% of our elimination product. Okay, so when we think strong bases, we have to see whether they're nucleophilic or not. If they're nucleophilic and we don't have too much steric demand, SN2 will be in competition with our E2 elimination. Okay, so let's talk about that. E2, by the nature of the two there, means it's a bimolecular reaction, which means the concentration of the base and the concentration of the substrate are in the rate law, okay? So if you double the concentration of the base, keeping the substrate the same, the reaction will double. If you double the concentration of the alkyl halide and keep the base the same, you will double the rate of reaction. If you double both of them, you will quadruple the rate of reaction, just like with your SN2. The only difference here is we have something that can act as a nucleophile or a base. And when we use it as the base, it's going to remove one hydrogen, one halogen, giving off, in that case, HBr or HCl, and forming our double bond. So that makes it a second order reaction, so that we call it a bimolecular. So E2 is a bimolecular reaction. Okay, so what's the mechanism? Well, being a bimolecular reaction, that means we have to have the base close to our substrate before we start. In fact, the base is going to be pulling on a beta hydrogen, and that beta hydrogen has to be opposite the or anti to our bromine leaving group. Notice how we're going to tug on this beta hydrogen here, and that if we look at our transition state, this hydrogen, these two carbons, and this bromine are all in the same plane. That's because we're going to move a total of 6 electrons around all at the same time. It's a concerted reaction. It happens all at the same time. So let's look at those different electrons that are moving around here. So the first electrons we're going to see moving around are the electrons, the lone pair from our base. Okay, they're going to reach out and start tugging on this hydrogen. Okay, that hydrogen that was bound to our carbon here is going to give up those 2 electrons right here. Oops. It's going to give up these 2 electrons, and those are going to form the double bond, the pi bond between the 2 carbons. Okay, so 2 electrons have come in, 2 electrons have moved over. The last 2 electrons are the ones we have to break the bond with the bromine here, and they go with the bromine, giving it a negative charge. Okay, so it's a concerted reaction where we have a total of 6 electrons moving around. At the end of the reaction, we have our alkene, our neutral base, it has been protonated, our base has been protonated, and our leaving group as an ion. Okay, so because it's a bimolecular reaction, if we look at the coordinate diagram, we have one hump, okay? And the activation energy is based on the type of leaving group we have, whether it's a good leaving group or a bad leaving group, and the strength of our base. So if we have a poor base, that's going to be higher activation energy. If we have a good base, it's going to be lower activation energy. All right, questions about our reaction diagram and the basic mechanism of E2. We're going to add a few more subtleties to this as we go. So understanding this right now is important. Okay, so let's move on. So we learned in the last chapter that there are different types of hydrogen. Okay, there's the carbon that we have the alkyl halide on, that we have the halogen on. We call that the alpha carbon because that's our functional group. And we know that the carbons next to that are our beta carbons. And on those beta carbons, if you have hydrogens, those are the hydrogens that are going to be removed during our elimination product. So it's always going to be beta hydrogens, but sometimes you can have a choice. Okay, so let's look at the choices that we have here available to us for this particular one. And if we look at number B, letter B here, right here, if we remove this beta hydrogen, notice that this one has a methyl group on it, and this one over here only has, only has hydrogens on it, right? So this is a secondary beta hydrogen, a secondary carbon, and therefore our beta hydrogen is on a secondary carbon. If we take that and remove this proton, that's going to give us our double bond between these two carbons. And what we'll see is in that reaction, we're going to get mostly that internal double bond because it's going to form the double bond in between this number 2 carbon and this number 3 carbon in our chain. Okay. So, and then of course you get your neutralized base and your bromide salt out of it. So what if we removed it from the other side? What if we removed it from the other side here? So this is going to be our primary right here. And when we remove it from that, that means our double bond is going to be between the 1 and the 2 carbon. Okay. So the double bond is going to be between our 1 and our 2 carbon, giving us a mono-substituted alkene. Okay. And what we see is that in the case of our elimination reactions, it's going to try and be the major product to remove the hydrogen from the higher priority carbon. So a secondary carbocation, a secondary beta hydrogen or a tertiary beta hydrogen. It's going to try to remove one of those first. And then a minor product is going to be removing it from the lower priority, either the primary or the secondary. So that means our major product is going to be the more substituted alkene. In this case here, our alkene is di-substituted because we have a methyl group on each side. Now remember the stability of our alkenes. And we looked at that by heat of hydrogenation. And we saw that the monosubstituted is the least. The di-substituteds are about the same. Tri and tetra are even more stable. So the more substitutions we can get in this, the more stable the product is, okay? And so this is what we call Zaitsev's rule, okay? Zaitsev's rule says you're gonna remove the hydrogen that gives you the most substituted alkene. All right, so why? Well, when we're starting to do this reaction and we're starting to pull off the hydrogens on there and we're moving our electrons around, the pi bond that forms has hyperconjugation with two different sp3 hybridized carbons bonded to hydrogen. If we have it on the other side, if we put it on the terminal side here, the hydrogens can't hyperconjugate back because they're out of plane with that pi bond, meaning that anytime we can get more and more of this hyperconjugation between the hydrogens on adjacent carbons, the more stable the compound's going to be. Okay, but it's all about removing one type of beta hydrogen over another type. And that's, you want to move the higher priority, the secondary or the tertiary if possible. Okay, so let's look at that as a function of this compound here. So even though there's 6 of these right here, there's 3 here and 3 here. So there's 6 of these hydrogens and there's only 2 of these hydrogens. Thermodynamically, it's going to preferentially remove these one of those 2 hydrogens to form our internal tri-substituted alkene. Okay. Now, if it removes any one of these 6 hydrogens here, it's going to give our less thermodynamically favored product this di-substituted alkene. Okay. So because it's selective about where it removes the hydrogen, we call this regioselective because it gives a specific, it'll put the double bond in a specific way as the major product, okay? So if you have a reaction that particularly lends itself to a particular type of product, we call that regioselective because it's going to preferentially pull off these secondary hydrogens instead of any other hydrogen. Okay, so let's look at it from an energy perspective, okay? So the idea is we do get some of each product, right? So there is a kind of a competition between pulling off the beta hydrogens on those primary carbons and pulling off the beta hydrogens on those secondary carbons. So let's look at the energy barrier to do that. It turns out because when you're forming this, we're pulling the hydrogen off here, off this side here, and these two methyl groups can start to hyperconjugate with the incoming double bond that's forming. It is going to be preferentially removed, and therefore it has a lower activation energy. Okay, and so it has a lower activation energy, and when we do that, it's going to give us the tri-substituted P, right? So, but let's say you're heating the reaction, and there is at least a few molecules that have enough energy to pull off the alpha hydrogen here. So it's a higher activation energy first. And so you'll have enough, just a little bit in that long tail of energetic material that will go ahead and go over our second hump, get to our second different transition state here, and give us our other alkene. Okay. But notice where they end up. Okay. Where they end up. When we have this lower activation energy right here, we also have the more thermodynamically stable. More heat was released during the reaction. Okay, so because it's more thermodynamically stable, it is going to be our preferred product here. But look, it also has a lower activation energy. Lower activation energy means faster. So it's also the kinetic product. It's the kinetic and the thermodynamic product. So that's why it's heavily favored in the reaction. Now, in this one over here, we have it's not the kinetic product because we had a higher activation energy. Sorry. It's not the kinetic product because it had the higher activation energy. And it's also higher in energy than the other product. So it's not the thermodynamic product either. So what it is it just happens to be that it took one of the other hydrogens, the less stable hydrogen, because it had enough energy to create that higher energy product. Okay, so it's all about the transition state and that activation energy. That's why you'll always see a little bit of both, even though it's, the difference in this activation energy is not huge. So you'll usually see both, but the major product is going to be the Zaitsev product, which is the more substituted product because it's more thermodynamically favored. All right, questions on that? Okay, so let's look at that transition state, okay? So one of the things we want to pay attention to is we need to have the hydrogen we're removing opposite the bromine we're removing because it's a concerted reaction. We have to move all 6 electrons all at the same time. So they have to be lined up just right to make it happen. And one of the easiest ways to look at that is to look at it as a Fischer projection, okay? I'm sorry, a Newman projection. I said that wrong all day yesterday. Darn it. Okay, so if we do our Newman projection right here, and let's go ahead and I'll remind you how to convert this into our Newman projection. We're going to be looking down this direction here. And so this is going to be our first carbon, and this is going to be our second carbon. So our first carbon has a propeller on it. The methyl group is back, so that's here. Hydrogen's there, and the hydrogen's up. Then we're going to draw our second carbon, carbon number 2. And this hydrogen's up, back, and this methyl group's up. So that's going to put a hydrogen here, a methyl group here, and the bromine here. Okay. So that's how to convert that structure into this. But look what we have now. We have number 1, the 2 methyl groups are opposite each other. So that's going to be probably one of the lower energy states to have because those are the biggest groups hanging off there. We want them opposite each other. But look what else we have. We have a hydrogen opposite the bromine, okay? It must get into this state where you have a hydrogen opposite a bromine, anti to it. So this is anti to the bromine, so that when we kick the electrons in, it'll kick the electrons out and all the electrons will move smoothly at the same time, okay? So as we're going through this transition state, we have to go from our sp3 carbons to sp2 carbons. And as we go to those sp2 carbons, we change hybridization of the bond that was bonding to the hydrogen. We change the hybridization of the bond that was to the bromine, and we end up turning the connected atoms into sp2 bonds, which makes them trigonal planar, and we get a p orbital available on both of the 1 and 2 carbons. Okay, so as it's forming that pi bond, then it's going to make our final product. Also, look at this. We can also look from our position here, especially on the Newman projection, that in this configuration, we're going to get the trans right here product. Because notice those methyl groups are already opposite each other. And when we form our double bond through here, those are going to be on the either side of that double bond. And therefore, looking at the Newman projection, we know we're going to get the trans product from this transition state. Okay. All right. So that having them opposite, you need to move it around, rotate it if necessary, to make sure you have this opposite state. And then the difference between the cis and the trans is going to be which hydrogen you're pulling off and where it's going to end up on which side of it. Okay. So part of that is because when we have that sp2 orbital is going to be, that sp3 orbital is, as that hydrogen's pulling away, it's changing hybridization, and it has to be, this is the actual big part of the orbital that's bonding to the hydrogen. This is that small part of the orbital that's facing away from it. And notice that as we're breaking this bond, the big part of the orbital is going to be on this side because the little part's here, because that's empty because it's taking the electrons with it. And notice how they're kind of lined up, so that as it hybridizes, they'll just both line up and make our good pi bond with good p orbital overlap. Okay. So that's another way to look at it on why the hydrogen has to be anti to the leaving group. Okay. The other way to think about it is that if we were doing it as an SN2 mechanism, we're going to be doing the same thing. We're again going to be trying to form a new bond here, which is adding electrons to that side of the orbital and then removing the electrons when the leaving group leaves. Okay. But in the SN2 case, we actually have to have them 180 degrees from the same carbon. In the E2 mechanism, we have to have them anti to each other across 2 carbons. Okay, so that leads to the stereochemistry. Remember, stereochemistry is all about fixed in space. When we have our double bond, we don't have free rotation. Okay, so now we have to look at our different conformations and figure out which conformation, number 1, can react, because we have to have a hydrogen anti. Number 2, what kind of isomer we're going to get. Are we going to get the cis or the trans isomer, or the E or the Z? Okay, so we can do that best with a Newman projection. Okay, so in the case of this Newman projection here, again, we have the hydrogen up, the methyl group back, and the hydrogen here. So that's this hydrogen, this methyl group, and this hydrogen. We look at the other side, we have bromine down, methyl group, and that. So we have our methyl group, our bromine, and our hydrogen there. And in this configuration, this is a good, favorable position, okay? Our hydrogen and our bromine are opposite each other. Our 2 methyl groups are opposite each other. So as it goes through that transition state, these 2 groups are going to come down and become planar. These 2 groups are going to come up and be planar, and we're going to form our pi bond above and below that plane. But we still have free rotation around that center bond, right, between those 2 carbons. So what if we rotated that around and made it into something that was sort of kind of, in an eclipse stage right here? So if we looked at the Newman projection of this, we would have a hydrogen, a methyl group, and a hydrogen, and then we're going to have bromine and a hydrogen. Oh, let me do it a different color so you can see the back one. Right here, we're going to have the rear carbon here, and it's going to have the bromine on it. It's going to have a methyl group, and it's going to have a hydrogen. So first, we have an eclipsed diagram here. This is not very stable. We have big groups kind of coming together. But the other thing we don't have is that we can't easily move all of those electrons around because they're pulling on sterically, they're pulling and tugging at the same place. Okay, so this is less favorable than this right here. Notice this would also give a trans product right here, but because they are not anti to each other, because they're eclipsed with each other, that doesn't make a favorable energetic response to being able to form this bond. So we always want to try to make sure we have them anti to each other to determine our stereochemistry. Now, one of the other ways to do it is, let's say we don't have them aligned at all, and we have this hydrogen here that is staggered with the bromine here. Okay, so it's gauche. The bromine is gauche to the hydrogen. Okay, again, we cannot form that pi bond. We need those orbitals to be aligned. We have the new pi bond forming would be in this axis. The new pi bond forming where the bromine's leaving is going to be on the other axis. Notice these aren't lining up with each other. Because they're not lining up with each other, they're not going to form a double bond in that configuration. Okay. So that's another explanation of why we always want to arrange our materials to the anti position, hydrogen anti to the bromine, before we figure out what the stereochemistry of our final product is. Okay. Another way to look at that is looking through it with the cyclohexane. With the cyclohexane, we actually don't have that free rotation, but we do have the ring flip. So let's look at it as a function of ring flip and not as a function of that free rotation. Okay. So whenever we have our double bond here, if we have it in the most stable configuration here, the largest group is in the axial position, but it can flip back and forth. The bromine's not that big, and so we actually have a significant amount in this axial position where the bromine is in the axial. And the product from either of these configurations being going through an E2 elimination is going to be cyclohexane. Okay, but which hydrogen is being removed? Okay, we have to go back and look at, can we have a hydrogen 180 degrees away from the bromine to be able to pull it off? So let's go ahead and convert our cyclohexane with the axial bromine to our Newman projection. Okay, so if we look down our, let's see, we're going to do 1 and 2. This is 1 and 2. We're going to have a 1 and 2 here. So we're looking down 1 and 2 in this direction here. Okay, so our eyes over here. And so we were having our hydrogen facing up toward us, and our axial hydrogen, this one right here, is up here, and our axial bromine is down here. Okay, so right away we're looking at this. Oh, we have these two CH2s. That's not very stable, but that's how it works in a cyclohexane. And the hydrogen A, the axial hydrogen, is 180 degrees away from the axial bromine, which means it's a favorable way to eliminate the hydrogen and the bromine with base. Okay, and so that would give us this product here. Okay, so let's do it so the bromine is in the equatorial position, because it's going to be more in the equatorial position. Okay, so let's go ahead and do that exact same thing, where we take our thing and we're going to look down this 2 and 3 axis. So we're going to look down 2 and 3 in this direction here. So we have our bromine off to the side. We have our CH2 over here, and our hydrogen is an axial hydrogen. And then the other methyl is here. The equatorial hydrogen is over here, and the equatorial hydrogen is over there. Okay, now, what do we see? We see there is not an axial, there is not a hydrogen 180 degrees away from our bromine. We have it gauche, we have it 120 degrees, we have it gauche. None of those hydrogens are removable to give us our alkene product. Okay, none of those hydrogens are 180 degrees apart from that bromine. Therefore, this particular flip does not undergo an E2. Okay, we have to wait for it to flip over to the axial bromine so that we can get this 180 degree between our hydrogen and our bromine. Okay, so we have to wait for it to flip back and forth, and only this configuration will undergo E2. All right, questions on that? So in the case of straight chains, we're looking for rotation, free rotation. In the case of cyclohexanes, we're looking at the ring flip. Okay, now when we have the ring flip, that means that as we start to substitute it here, we're going to have to look at, are we forming that Zaitsev product that we're hoping to have, the more substituted one. If we can't get a hydrogen and a bromine opposite each other to form the more stable one, we might not be forming it. Okay, so let's look at this. So let's look at this example here. Okay, so what we did was we put a big T-butyl group on here. And if we look at it right over here, and so it's going to prefer to be in that equatorial position. Okay, now we have a methyl group here going up and a bromine going down. So if we redrew that on our side view right here, we're going to have the methyl group is axial, the bromine is axial, and the T-butyl group here is going to be equatorial. Okay, so this is probably its most favorite state. Okay, so now let's look down each of these bonds and find out which of these configurations can actually do an elimination. Okay, so we're looking for where the hydrogen is going to be removed. Okay, so if we look down this the two, that's labeled wrong. Let's see, the bromine is on the 1. Yeah, so this is the 1 and this is the 2. Yeah, we're looking first down the 1 and 2 bond. It's labeled 6 for some reason. We're looking down this one right here during that 1, 2. We have a bromine is going to be axial and our methyl group is axial. So that particular carbon here, we cannot remove a hydrogen from the number 2 carbon because that number 2 carbon, the number 2 hydrogen right here is gauche to our bromine. Okay. Now, if we did do that, we would have our more substituted product because we'd have the double bond in this area here. But we cannot do that. We will not form that product because we don't have a hydrogen 180 degrees. Okay, so let's go ahead and flip it to the less stable configuration where our T-butyl group is now in our axial position. Okay, once we do that, if we look down our 1,2 bond again, what we see here is that we have a bromine and it's either gauche or 120 degrees away from hydrogen. So that hydrogen can't be removed either, okay? So we cannot remove the hydrogen from this carbon with the methyl group, that number 2 carbon. Let's look at the other way, okay? So if we look down the other way, in this configuration, we can't remove either of these hydrogens either because we have a methyl group, which is this methyl group here, opposite the bromine. So neither of these configurations will give us product. And this configuration won't give us product, which means all of our products come from this one configuration, and that gives us one final product, the less substituted alkene. Okay, so it's not following Zaitsev's rule because it's limited in its modes of freedom. And by drawing our Newman projection, we can figure out which of these configurations gives us which product. Questions on that? All right. Okay, so what if we flipped it around a little bit? Could we get different products? Yeah, because if we flipped it around so they're all up right here and we redrew that such that, okay, the first configuration is going to be with our T-butyl up, our methyl group up, and notice that that bromine is the only one that's equatorial now. The methyl group and the T-butyl group are all in the axial position, and this hydrogen would be the hydrogen that was pointing down. So that puts us as our bromine in that equatorial position. Okay, so when we draw our configuration here, in this right here, if we look to this direction here, that's this Newman projection, and it does have the bromine opposite a hydrogen, meaning we can form a double bond between where the bromine was and that methyl group. So we can get them more thermodynamically favored from this interaction. Let's go ahead and look at the other direction. Let's go into this direction. We have a bromine opposite of that. So we can form the less thermodynamically stable product, because in both cases, we have a bromine, the leaving group, and the hydrogen anti to each other. Okay. So let's flip it to where it's probably going to spend more of its time. We have the T-butyl group in that equatorial position. Okay. Now, if we look at it, we have, look down that bond again, we have the bromine and a hydrogen opposite each other, and that's going to give us the more substituted product. But if we look down the other direction here, we still have a bromine next to a hydrogen, and that's going to give us our less substituted product. So in both configurations, either product can be formed, okay? But you'll only see that if you draw it as a Newman projection. Questions on that? So, okay, another question. Because we can do either one of those, which do you think of those is the major product? The more substituted, the tri-substituted, or the di-substituted? Right, the more substituted is going to be our major product, but they're both available because that transition state lines up hydrogen with the leaving group and gets us to that. All right, so the trans isomer is usually produced in the greatest yield. The reaction is not necessarily, the reaction is not only regioselective, meaning it's going to preferentially form the more substituted alkene, but it's also going to give a stereoselective. It's even going to form the more thermodynamically stable one. So let's look at that. Even when we take this, our methoxide as a strong base, our secondary bromine here, we're going to form some of it where we remove it here, and that's going to give us this product. We're going to do some of it where it removes it here, and in this configuration, that would give the trans product. And then we're going to have some of it where it has freely rotated around, and now our methyl group is down here, and that would give us our cis product. If this rotated over here, that would give us our cis product. So that being said, that each of these things can form because of all the hydrogens we have available to it. But look at our product ratio. We have a little bit of that, even less of that, and we have predominantly the double bond as the trans. Notice it's 82% just the internal double bond, the more substituted double bond, but it's 67% of the entire reaction mixture is the more thermodynamically stable. So it's not only regioselective about which hydrogen it pulls off, but it's also stereoselective, and where the product is going to be favored for one product over the other. Okay. So if we look at why the trans product would dominate over the cis product, we have to go back to our Newman projection again. So in the case of this right here, we're going to look down this axis right here. And so we have our hydrogen A, we have CH3, we have HB, we have our rear atom here, we have a CH3, and we have our bromine here. Okay. So when we take this and we have our hydrogen and our bromine anti to each other, and notice that the methyl groups are anti to each other. So that when we do our elimination, it's going to flatten out such that we have a methyl group, a double bond, and a methyl group. Okay. So in this configuration, this is really stable. This is our methyls are anti to each other, and our hydrogen and our bromine are anti to each other. Let's rotate it a few degrees. Let's rotate it 120 degrees around here, and that's this configuration here. all we did was rotate that. So we pulled the methyl group forward. The B hydrogen is now up and the A hydrogen is in the back. In this case, the B hydrogen is the one we're going to use. So let's go ahead and draw our Newman projection here. We have our HB. We have CH3 over here and an HA over here. Let's draw the rear atom right here. And so we're going to have an H over here, a CH3, and our bromine is going to be there. Okay. Now, immediately see that the methyl groups are now Gauss to each other. Okay. Our hydrogen and bromine are 180 degrees, so it still can react to give us our elimination product. But our methyl groups are starting to butt up against each other, so it's going to spend less time in that configuration. That's why the trans product is going to dominate in this elimination reaction. Okay, does that make sense? Okay. All right, so the best way to do this to figure out which isomer you're going to get is you're going to use that Newman projection to do it. You're going to try to draw it such that the two largest groups are going to be anti to each other. In this case, we're using methyls. When those methyls are anti to each other, we get the trans isomer because we're not going to be breaking any of these bonds. We're just going to be flattening out so that these come down and become planar. Okay, so that planarity, they're already on either side of that incoming bond that's being formed right here, and that gives us the trans isomer. If we have them in that Gauss situation, again, they're not going to break those bonds. They're just going to flatten out. They're going to come down and get planar again, and that would give us the cis isomer. Okay. All right. Okay. So because there's an energy barrier to have that in a the Gauss configuration is higher in energy, we actually have a different kind of reaction coordinate diagram. Okay, so we have the potential energy of the material here in its most stable configuration, its anti-configuration. This is going to be the more stable or most stable of the rotational isomers. And therefore, we have an activation energy to do our elimination. Activation energy right here. Now, we have the exact same chemistry. We have the exact same material. So the activation energy is actually exactly the same. However, we started at a higher energy level. So we have to get from that higher energy level up to that activation energy. That means that it's a total energy required to get that Gauss product to react is higher than the total energy needed to get the trans or the anti configuration to react. Okay. And when it does, it forms the less thermodynamically stable product. But when it goes with the anti configuration giving us the trans, it actually gives us our most thermodynamic. So in this case, the trans isomer is the kinetic isomer as well as the thermodynamic isomer, because it has, even though they're the same amount of energy here, it's already starting in a higher energy state. You had to give it more energy than you did to the anti-configuration for the methyls, and therefore it's the slower reaction. All right, questions on that? Okay. Let's see. Bueller, we wait here. Okay. All right. So another way to look at this is to actually go ahead and look at it as a Fischer projection. Okay. And sometimes when you do it as a Fischer projection, some people like this better because you can see how your regiochemistry changes. Okay. So let's start with that Fischer projection. And remember that in a Fischer projection, these are going down, this is in a straight line, and this is going down. So that carbon chain, the longest carbon chain is that long vertical axis. And then these groups are all facing up. Okay. So when we translate that, we're going to have our carbon down, our carbon flat, and our carbon down. That's this methyl group is here, that's this methyl group is here. Okay. So that's just translating that two-dimensional object into our three-dimensional object. When we do that, we see that we have a bromine and a hydrogen here, but we don't have a hydrogen or bromine, a hydrogen opposite our bromine, okay? In this case, we're using deuterium to mark it as different than hydrogen, okay? So in this case here, we have to rotate our hydrogen, or in this case, our deuterium down to be anti to our bromine. And when we do that, we see that that methyl group goes back and ends up in the back configuration. This methyl group is now in the front configuration. That's going to give us the trans isomer, okay? So by removing the deuterium here, it's going to give us the trans isomer. However, if we rotate it around and remove the other hydrogen, what it's going to, not the deuterium, but the hydrogen here, we're actually looking at this. The methyl group is now on the same side as this methyl group, and therefore it's going to give us the cis product. All we did was rotate this 120 degrees to give us our methyl group facing out again, and we still have a hydrogen that's anti, and that anti-hydrogen allows it to eliminate freely. Okay. So what if we changed it a little bit and we did it with a different isomer? We're going to do that same conversion. The methyl groups are going to be down. Methyl groups are going to be down. These two carbons are going to be in the plane. So that gives us this right here. We have a bromine facing up and a bromine hydrogen there. So that gives us a bromine up and our hydrogen there. And our deuteriums on the other side now, which are deuteriums in the back and hydrogens here. So in this configuration, if we rotate it around to give us that deuterium as our leaving hydrogen, we end up getting the cis isomer. And if we rotate it 120 degrees to give us the other isomer, so removing the hydrogen instead of the deuterium, notice the methyl group is now back because we rotated it 120 degrees that way. And we get to have our hydrogen anti to our bromine. It gives us the trans configuration. So you can do it by Newman projection or by Fischer projection, but choose one or the other because it makes it, it's hard to go between the two. To give us what our stereochemistry is, what our final products are going to be. It's especially important with our chiral materials because you're going to have 3 different groups on those, on that. You have a possibility of having different configurations based on what the groups are, because this is deuterium and it's different than the hydrogen. So we can track it. All right, so that's what happens when we have strong nucleophiles that are strong bases that aren't very big, okay? We typically get the Zaitsev's product. We get them more substituted whenever possible. In the case of the cyclohexanes, we saw we couldn't even get the configuration right to get that more substituted product. So we have to pay attention to that. But what if we wanted actually to make the least substituted one? Well, we have to change our chemistry a little bit. And the way we change our chemistry is by changing the size of the base, okay? So the Zaitsev's products are those that use small bases that are strong, okay? To get the other regioselective product, the less thermodynamically stable product, we call that the Hofmann product, okay? So in this case, we're gonna go from a small strong base to a really big strong base. So when it's really big, it can't get into that secondary hydrogen and will preferentially remove a primary hydrogen. So let's look at that in a little detail here. So our ethanol and methanol are used to make our Zaitsev's products, okay? The more thermodynamically stable because it's going to remove that secondary hydrogen, that more substituted carbon, the hydrogen off the more substituted carbon. But we still make a little bit of this because of statistics, that we have 6 of the other hydrogens and only 2 of these. So, sorry, drop my pen. What happens when it starts to get so big that the methyl group over here is crowding out the base trying to remove the hydrogen here? Well, if it's crowded out because of that, it's going to go to the least sterically hindered side of the molecule. And when we do that, we see that when we have something like T-butyl group here, Our Zaitsev product drops down to 28, and our less stable, our Hofmann product, the least substituted product, is now the major product. Okay, so when we're looking at our in our activity next week, we want to look at the type of base we're using. The type of base we're using is going to tell us whether we're going to have the Zaitsev product or the Hofmann product. Now, if we got it even bigger and bulkier, now remember this, because these have free rotation, they can swing around like propellers. So that makes it even bigger. We drop it down even again, almost 92% the less stable product, because we use this huge bulky base. Okay. And if you look at the size here, you know, this is the anion, this is the part that's doing the base part. And those methyl groups take up a significant amount of room. And then they're solvated on top of that. And just adding that extra methyl group here makes it even bigger and bulkier. Oh, no, these are more, yeah, the hydrogens, oh, sorry, this is the substrate. This is our bromine here, and then these methyl groups are more exposed than just these two hydrogens here. So it's going to come in and attack this one of these 6 hydrogens here and eliminate our bromine from this side. Okay, so do we see why that big base is going to reverse our product ratio? Okay, well, let's do a little bit more about the Hofmann elimination. And so we have a rule, okay? The removal of a secondary hydrogen is more sterically difficult than moving a methyl hydrogen when a hindered base is used, okay? So that means we lead to a different transition state, and therefore, when we have these big bulky bases, we actually end up with the less stable product as the major product. So in this case here, notice how this base is written. 3 methyl groups on a carbon, O and A. So that tells us it's T-butoxide, sodium T-butoxide. Okay, it's so big that it can't come over here most of the time and ends up taking away the hydrogens on those less substituted, the primary hydrogens instead of the secondary hydrogen. So when it takes a primary hydrogen, we end up with our di-substituted alkene. When it takes that secondary hydrogen, we end up with our tri-substituted alkene. But because our base is so big, the di-substituted is the major isomer. And that's what we call the Hofmann rule. So basically, they're tricking it into making the less thermodynamically stable alkene by not allowing it to preferentially remove our secondary hydrogen. Okay. And it has everything to do with sterics, okay? Remember, almost all of our reactions have something to do with sterics or electronics. So let's look at the sterics of that. So if we have our base starting to pull on one of these hydrogens, we have to have that hydrogen. And if we start with that secondary hydrogen here, we have the base itself is really big. It's starting to butt up against the methyl groups over here and this methyl group over here in space. And so it takes more energy for that base to get close enough to start pulling on that hydrogen. If it takes more energy to get to be pulling on that hydrogen, it's a higher activation energy. Okay, so, but what if we attack the other side? What if we attack one of the hydrogens on these methyl groups over here? If we look at that, we have 2 hydrogens that are small and only 1 methyl group and 1 CH group over here. So the dominant steric factor is this 1 methyl group. We still have those smaller groups here, but that's less sterically demanding. That means it's going to take less energy to get to that activation energy. So we have a smaller activation window. And so we're going to use that mechanistic pathway. Okay. So if we use that, we're taking a hydrogen off, and we're getting the less stable thermodynamic product, okay, because it's less substitute. So what does that mean? That in a Hofmann elimination, we have the kinetic product, but not the thermodynamic product. So this is a kinetically driven system, okay? If you do heat it up a lot, you might get some molecules to do this, and you can get the more thermodynamically stable, but it's always going to be the minor product because it's the slower reaction. This reaction is the kinetic reaction, and it's going to happen faster. The other one is the thermodynamic reaction. It's going to happen less because of the higher activation energy. Question on that? Okay, so let's compare and contrast the Zaitsev's rule for the Hofmann rule. In Zaitsev's rule, we're trying to form the more thermodynamically stable product, right? And it just so happens that because it's easier to remove a hydrogen from a secondary carbon than a primary carbon in this case, we end up having a lower activation energy for removing the secondary hydrogen. And when we do that, it gives us our more substituted alkene, which gives us our thermodynamic product. So in the Zaitsev's elimination, we have the kinetic and the thermodynamic product. But we do have a competing one here because we have 6 of these hydrogens out here. And we have just a little bit higher energy barrier. We can form some of that, which is the less thermodynamic, but it's a higher energy barrier, so it's slower. And it's slower, meaning it's the minor product. Okay. In contrast, we have the less thermodynamically stable one having the lower activation energy. And the lower activation energy tells us it's going to be faster. And so we have the less stable one actually forming much, much faster than the more stable one. Therefore, we end up with the kinetic product as our major product and our thermodynamic product as our minor product. Notice in this one right here, this is both our thermodynamic and our kinetic products. Okay. So Zaitsev is thermodynamic and kinetic. Hofmann is all about being kinetic. All right, questions on that? Okay. So let's talk about regiochemistry. If the size of the base controlled the product we get because of sterics, what about the size of the leaving group? Okay, bromine's not our only leaving group. There's a lot of other leaving groups, especially things that are like protonated water. A protonated alcohol, it leaves as a neutral species. We can do a bunch of different things like that where we can have a quaternary ammonium salt where we have this as a leaving group or this as a leaving group. Now, notice that we couldn't just remove that. If it only had 2 methyl groups on there, it'd be leaving as a nitrogen anion. That nitrogen anion is too strong. But because we have 4 groups on nitrogen, when it takes the electrons with it, it leaves as a neutral species. So that makes it a good leaving group because it leaves as a neutral species. However, it's a big group, okay? So when we look at this, we have to look at, where is our base coming in and which base are we using? Okay. So in the case of using something nice and small like methoxide here, we actually can look at the secondaries are the ones we think we want to remove. But again, we have to have that anti to the leaving group here. It turns out when we have a big bulky leaving group, we end up getting the Hofmann product instead because of the sterics of the system. And in the case of this right here, this leaves as dimethyl sulfide, a neutral compound, which makes it a good leaving group. It does the same thing. Having a big bulky leaving group switches you more to the Zaitsev product, even if you're using a small base. Okay. So a large, big leaving group does control the regioselectivity of where your double bond will form. It's going to form the less substituted double bond and your major product. Questions? So we talked about electronics and we talked about good leaving groups, bad leaving groups. We talked about how to look for where the hydrogen and bromine have to be, or the hydrogen and leaving group have to be. Now we added sterics to the system and it changed everything, right? It went to the other non-thermodynamic product. So if you have small things, small leaving groups and small bases, think Zaitsev. If you have large bases or large leaving group, think Hofmann. Okay, so an example of how this would work is, let's see, it's also a function of your idea of how big something is, okay? So, or how good your leaving group might be, okay? So in the case of iodine, iodine is iodine is a big polarizable, easy to leave group here, okay? And so if we have iodine on our system, it's going to preferentially remove a secondary right here, giving us the more substituted product here. Bromine and chlorine, they all do this. They all give the more substituted product. However, fluorine is not as good a leaving group as the rest of them, okay? And it actually changes the product ratio. Fluorine is the only one that when you remove using an elimination reaction actually provides the Hofmann product instead of the Zaitsev product. And it all has to do with that transition state of the leaving group. Okay. The carbon-fluorine bond is much stronger than the other halides there, meaning that it's going to have to break more of the carbon-hydrogen sigma bond before it's starting to break the carbon-fluorine bond because it's a stronger bond. So even though we're doing it in a concerted reaction, the hydrogen is more removed in the case of this system here. And as we're starting to remove it, we're leaving electrons here and we're getting our partially positive charge on this side over here. Okay. In the case of our bromine's a much better leaving group. It has a weaker bond, and we're actually forming our negative charge on the bromine, not on a carbon right here. So it turns out that when we do this, we're forming a little bit of negative charge on a carbon. Okay. We've talked about carbocations already, and that was that tertiary carbocations are more stable. Okay. Well, when we're talking about anions, it's actually the opposite. So when we have a carbanion, it's actually more stable with less substitution. Okay. So because we're forming a little bit of negative charge on this carbon, we want to have a less substituted carbon in the system because these are more stable, and as you substitute it, they become less and less stable. So in this configuration, we are having to pull the hydrogen off more, create a little bit of carbanion character, negative charge on carbon, before this bond will even start to break. And that's why the fluorine prefers to have our primary hydrogens removed instead of our secondary hydrogens. If we tried to pull the hydrogen off of the secondary hydrogen, we'd have a secondary carbanion starting to form. Our secondary carbanion is less stable than our primary carbanion, and therefore it's less favored electronically. All right, questions on that? So this is going to the bond stability. Okay. So let's see what we have here. Okay. And then this is, this is showing you both of the pathways possible here. If we form the primary carbanion right here, we're going to end up with the more stable transition state, which gives us the less thermodynamically stable product, the Hofmann product. If we go to pull off the secondary hydrogen here, that would give us a negative charge on our secondary carbon, which is less stable. That would give us our Zaitsev product, the more substituted product. But because of the strength of that fluorine bond and because of the nature of forming a negative charge on carbon, we want the negative charge on carbon to be on the least substituted carbon whenever possible. Then that explains the product ratio between having the mono substituted versus the di substituted. Okay, Questions on that? All right, that is the end of module 7.2. Okay, and we have some time, so we can start on module 7.3. Okay, so what we're going to do now is, this is kind of a primer for what we're going to be doing for our reading. This made so much more sense than when I read it. Oh, yes. Yeah, it's all about getting it in a perspective of saying, oh, why, what's different? What's changed? And this is the first time we introduce a carbanion as well. So, okay, so module 3 is all about figuring out which mechanism you're going to be using. Okay, SN1 and E1 are always in competition, right? Because they can, they both go through that carbocation, right? E2 and SN2 can have competition if you have a good nucleophile and a good base. But if you have just a good nucleophile, it's going to go substitution. So let's talk about how to look at a reaction and kind of get it broken down into figuring out which mechanism it will use. Once you figure out which mechanism you use, you'll know what the major product is. Okay, so one thing we want to look for is we want to look for the nucleophilicity and the basicity, okay? If we have a very strong base, we can start to say, oh, elimination is going to be one of our products, okay? So in the case of our good leaving group, we'll have a competition between our elimination product and our substitution product, okay? So, but what if we have a good nucleophile? So what if we have a weak base and a poor nucleophile, okay? Well, a weak base and poor nucleophile tells me that we're probably going to end up going through a carbocation because we don't have enough to pull a hydrogen off, and the nucleophile is not strong enough to react by itself. So think carbocation, like water. Water is a weak base and a poor nucleophile, okay? So we have to think about the nature of this. Now notice the strong bases in this configuration here have negative charges on them, right here. All of our strong bases have negative charges on them, okay? And our good nucleophiles typically have negative charges on them as well. So when we start looking at strong base and nucleophile, start thinking bimolecular reactions, okay? But then you'll figure out which one's which based on the base strength versus the nucleophilicity. Now, whenever we have a weak nucleophile, it's not going to react directly. It's going to wait until the carbocation is formed. So when we have weak base or poor nucleophile, notice it doesn't have a charge. It's just something with a lone pair. It's not going to directly attack our species. It's going to wait around for the carbocation. And in that case, because it's a weak base, it's going to give you either the substitution product or the elimination product. And they're going to be in competition. Okay. Because once you get that carbocation, whichever is going to react, if it pulls on the hydrogen on an alpha beta carbon, then it's going to do the elimination. If it actually uses its electrons to form the bond with the carbon here, it's going to form the substitution product. Okay. So that's the first thing to look for, okay? And at the end of this, I have a table of strong bases and, there's it, oops. Oh, I have a table somewhere. I'll show you a list of strong and weaks, okay? So that's the first thing we look for, okay? Base strength, nucleophilic strength, okay? Strong bases are going to favor E2 reactions. Good nucleophiles that aren't strong bases are going to favor substitution reactions. Weak bases and poor nucleophiles are going to favor a competition between SN1 and SN2. Okay, so let's go back to thinking about nucleophilicity and basicity, okay? So nucleophilicity in our SN2 reaction, if you remember, hopefully, is that high affinity for carbon to form that bond that is the backside of the sp3 hybridized bond that's holding onto your leaving group, okay? So that means that we have things that are good nucleophiles are negative charges, things that are very weak bases things that can be strong bases, weak bases, but notice all of the strong nucleophiles have negative charges. And then water and alcohols are kind of low. So that's just nucleophilic strength. That's the desire to form a new bond with carbon. Okay. Basicity is measured by our pKa. And if we look at our basicity here, it kind of looks like it might be going in reverse order here, but it's not that. It's all about what the pKa of the conjugate acid is. The higher the pKa of the conjugate acid, the lower the pKb. So these are negative because it's 15 and 16 respectively. So subtract 14, and so our basicities, our kb's, our pKb's are going to be negative. Then we get to there, the pK of water, of protonated water is around -1, so that's going to be next. Our alcohol is next, and then of course these were our strong acids. Those were our strong acids, so they're going to be our weakest bases. Okay, so nucleophilicity is all about forming that new bond with carbon. Basicity is all about looking at the pKa of the conjugate acid and converting it into our pKb. Okay. And then things that are very weakly basic, like chloride or acetate ions, are weakly, more likely to do an SN2 reaction because of that high polarizability and weak basicity. Okay, so let's look at it from the electronics perspective, okay? Compare and contrast our nucleophilicity with our basicity here. Okay, so if you have something big and fluffy, like an iodine, that is weakly basic because the conjugate acid is so strong, it's going to change its interaction during that reaction with the SN. It's going to favor an SN2 reaction because it can start to form that bond with the carbon because of its high polarizability, and it's going to help eliminate, it's going to help the leaving group leave. So because it's polarizable and because it's a weak base, it's going to favor SN2 reactions. So it's favoring an SN2 reaction because it's a weak base, but it's, remember, polarizability is one of those things that increases nucleophilicity. The more polarizable you are, the more diffuse your charges, that increases your chances of SN2. Okay. So the size of the nucleophile base also plays a role here, right? Because if we have a small base that's a good nucleophile, we have a competition between our elimination product and our substitution product. However, when you have a small base and an primary alkyl halide, the primary product is going to be your SN2. So think primaries react faster than secondaries react with tertiaries in substitution reactions. So in this case, it's looking at the nucleophilicity of the reactant, in this case, methanol, or methoxide, sorry. So it's small and it's a strong base, but it's also a strong nucleophile, but we have a primary carbon. When we have that primary carbon, the substitution reaction is faster than the elimination reaction, and our SN2 is our major product. Let's flip that around. Let's keep the substrate primary, but let's turn it into a big bulky base, that T-butyl base. So this is the T-butoxide right here. We can completely flip the system here, okay? We have a hindered base. That hindered base makes it less nucleophilic. The bigger the anion, the bigger the molecule, the less nucleophilic it is, okay? So it's going to favor the elimination product because it's going to act more like a base and less like a nucleophile. But we do have a little bit of the SN2 as our minor product because we have a primary alkyl halide. If we had a secondary alkyl halide, this would drop almost to 0. Okay. So in the case of these primaries, if it's small and it's a strong base or a strong nucleophile, or sorry, if it's a strong nucleophile, substitution is going to be the #1 thing you're going to do. If you have a big bulky base, elimination is the primary mechanism you're going to go through. All right, so, and just to visualize that size issue here, when we have our big bulky base that has to be solvated anyway, as it's coming in to try to create that new bond, it's being pushed away by the electron-electron repulsion of the things around it. Okay, so it's, instead of coming in and attacking at the opposite side of our leaving group here, it's already in position. It's just going to pull off one of the hydrogens instead. Okay, so because it can't get all the way in here to form its bond, it's going to say, well, I'll just act like a base, pull this off. That'll kick into our concerted reaction and give us our elimination product. Okay. Notice it's coming from basically the same pathway. Okay. So, but if we had a nice little small one, it would just jump right in there and do our substitution reaction. Okay. Let's look at the rates of reaction based on size. Okay. So usually the big bulky groups are going to slow the reaction down, okay? Because it takes more time to get enough energy on those big groups. Remember, they have to have enough kinetic energy and enough things hitting together. They're bigger, they're harder to get fast enough, and they diffuse more slowly in your solution. So in the case of methoxide versus T-butoxide, the methoxide is a much faster reaction to do the substitution product versus the T-butyl group. It still goes, but it's a much slower reaction. Okay, so because it's a much slower reaction, methoxide is actually a much stronger nucleophile. Okay, but T-butoxide is a much stronger base because it's going to act less as a nucleophile and more as a base, but the methoxide is going to act more as a nucleophile and less as a base. All right. Okay. In most cases, the steric hindrance does not affect the basicity because basicity involves attack on a hydrogen. So because we're not trying to squeeze into this little space here, right here, we're actually pulling on something way out here. The base strength is only slightly higher for T-butoxide because water's around 15, methanol is around 16, ethanol is around, T-butoxide is around 18. So it's a little bit stronger base. And so the fact that it's big and bulky here does not mean it can't remove protons like here or here, but it does mean it's not going to come in and do our substitution reaction. So that means that big bulkiness is taking down the nucleophilicity, but it's not affecting the base strength because that's not a requirement for removing a proton. We don't have to form this new bond in that way. We're just reaching out with our electrons to pull off a small atom. Okay, let's see. So I kept saying that nucleophilicity is different than basicity. Okay, so the reason we have that is that nucleophilicity is a kinetic phenomenon quantified by how fast the reaction goes. Okay, so that's how we measure it. We actually say, okay, this much in here, it goes that fast, this more goes this fast, add some more, it goes this fast, right? So it's a kinetic phenomenon. So we're looking at the products formed at what rate. Basicity and acidity are equilibrium. We measure that at equilibrium. So it's not about the kinetics of the system. So that's a major difference between the nucleophilicity of a system and the basicity of a system. The basicity of the system is where we measure our equilibrium constant. We measure our pKa's basically at equilibrium. So it's a completely different way to look at it. So nucleophilicity is kinetic. Because we're at equilibrium, basicity is thermodynamic. All right. So let's talk about some common really big bases that we'll see that promote a Hofmann elimination. Okay. So in this case here, we have our classic, which is T-butoxide right here. It had a pKa. Oh, sorry. Thank you. So Sheila has just told me that it's actually just past 9:20. I apologize. We'll pick it up here on Tuesday, and we have our activity at the end of that, okay? So thank you very much. I'm gonna go ahead and stop recording. If you wanna stay behind and ask questions, please do.